Today we are going to discuss lab number 5 of linear control system. Title of our lab is Mathematical Modeling of Physical System. In this lab we are going to discuss how we can derive a mathematical model from any physical system and how we can implement or solve that mathematical modeling by using MATLAB. So let's start with the example. We have we have here mass spring system model. You can see in figure 5.1. So here a mass is attached to a spring. We have applied force Fa of t. You can see in the right hand side direction. So there are two external forces will be act upon this mass, and these forces will be spring force and frictional force. As you can see, the direction of these forces are opposite because we are pulling mass in this direction, so spring and friction force will try to pull the mass in the other direction. So I hope the scenario of this figure is clear to you all. Now we have to derive its mathematical model and then solve it in the MATLAB. So here we have some quantities like acceleration. We can see there is a displacement. Whenever we applied a force on a mass, it will cover some distance in a particular direction because force is a vector quantity and its direction is shown by this arrowhead. So here x of t is the displacement. You can see over here as well. Velocity is equals to the rate of change of displacement. So I can write this v equals to first derivative, which is the rate of change of displacement, and acceleration is equals to the rate of change of velocity. So if we would like to convert this acceleration into the displacement form, so we have to take its double derivative. So velocity equals to the first derivative of displacement and acceleration will equal to the second derivative of displacement, because acceleration is by definition is equals to the rate of change of velocity. So I hope this supposition is clear to you all, or these values are clear to you all. So here we have equation 5.1, which is a law of physics. Like if we applied any force, so it will be equal to the sum of individual forces act upon that body. So we have three different forces in this case. The first one is the mass multiplied by acceleration, the second is the frictional force, and third is the spring force. So in this case, for frictional force, we know that it will be equal to the frictional coefficient multiplied by the velocity. We know the value of velocity because we want to convert each quantity into the displacement. So we have to put the values in the form of displacement. So b multiplied by v equals to dx over dt. Here we have b as well. Then we have spring force. Spring force will be equal to the spring constant multiplied by the displacement. Now we are going to put these values in equation 5.1. You can see mass constant equals to the m, and acceleration is equals to the d, second derivative of displacement we have supposed here. Then we have frictional force, so it will be equal to the b. From this equation, b multiplied by v, and v equals to the dx over dt. And the last quantity we have the spring constant or spring force, which is equals to the spring constant multiplied by the displacement covered. So here you can see we have developed a relationship between applied force and the displacement x of t. This equation, you can see it's a linear relationship between these two quantities, but in real scenario these relationship will be more complicated and can be linear. So if they are and can be non-linear. So if they are non-linear, then we have a quantity y as x raised to power, which shows that the spring force or the frictional force can be a non-linear quantity, and it will depend on the value of y. If we would like to observe the results in the graphical format or non-linear relationship, so these quantities will depend on the value of y. As y changes, the response will also get changed. So to identify whether the equation or the system is linear or non-linear, we have already discussed the properties homogeneity and superposition. We have to satisfy these two properties if the system is to be a linear. So this is a non-linear relationship. Now, solving these differential equation on MATLAB, our focus is to solve these equation by using a MATLAB tool. So here we are using we are discussing two different examples. First, we have a speed cruise control example. Here you can see that from the same equation, from the same above equation, we have discussed or derived equation number 5.2, this one. This equation, here we have supposed the spring force F of S equals to 0. So by substituting F of S equals to 0, we will left with the two quantities. So here we have MA force and frictional force is equal to the total applied force. Now we are going to solve this equation by using MATLAB code. So we have to find out the relationship of velocity with the applied force. So we have converted the displacement into the velocity format. So second derivative of displacement equals to the first derivative of velocity. You can see in equation 5.5, and first derivative of displacement will be equal to the velocity. So here we can write BV. I hope this equation 5.5 is clear to you. We just put the value of velocity, or we just replace the displacement with the velocity in this equation. So now we are implementing this equation on MATLAB by using ODE, ordinary differential equation function. I will let you know about this command later on. So first we will suppose the values of the constant like mass, frictional constant, applied force, and then we have to put the equation. So for finding dV over dt, we take this PV on the right hand side, so it is positive become negative, and m will be divided with FA of t minus BV. So here you can see the same equation written in the coded format. So in the next step, this section is basically a function. We have created a function on MATLAB. The function name we are using is cruisespeed.m, and by creating any function on MATLAB, you have to write function and then define its parameters, like function dv dt equals to cruise speed, which is the relationship between time and velocity. So creating function MATLAB gives you a handy tool to call it again and again. You don't need to write the you don't need to write this whole code again and again, but just you can call this name cruisespeed.m, and it will call this function by itself. So it is a good advantage in MATLAB. Second, we have now we are going to solve this equation. So we have supposed the initial velocity equals to 0, and now we are using ODE function. This is the function name which we have declared in the start. Here you can see cruise_speed.m. So calling this function cruise_speed, and this is the time spent from where, because we are solving it with respect to time, so this is the time limit. You can also change this limit if you are going to observe on greater span like 250, 500, or lesser span like 10 or 50. So here we are using time span from 0 to 125, and initial parameter or initial condition is v0, which is equals to 0. Now we are plotting this relationship with respect to time. Grid on basically gives you a graph on the grid, and we have declared the title of our graph. So it will show a graphical format. It will show you the result in the graphical format, and you can see here we are also using dsolve for the same equation. Dsolve, it's another command. I will tell you the difference between, it will also show you the result of this equation, but difference between dsolve and ODE45 we will discuss. But here remember, we are using two functions. One is ODE45 and second one is dsolve to solve this particular equation. Now we will discuss second example, mass spring example. So from the same equation, for the non-linear one, we have equation number 5.4, you can see. So from the equation 5.4, now we are solving a mass spring system, which is the second order differential equation. Here we use supposition method to derive the equation for dx of t. So here we assume x of t equals to x1, which is our state variable, and x2 equals to first derivative of dx of t. So in this way, first derivative of x1 over xt will be equal to the x2 from this relationship. And if we want to find out dx2 of t over dt, which is this, so we have to basically shift all these two quantities on the right hand side and divide by this m, because d double derivative of displacement will be equal to the first derivative of this x2. I hope this supposition is clear to you all. So here you can see we derive this dx2 over dt by shifting this 2 on the right hand side and divided by m, written over here. Now we have to solve this differential equation. So we use the same method we use to create a function first, which is mass_spring function name, and we created this function by writing function and declaring its parameters. So here we are going to solve with respect to displacement with respect to time, and then we have suppose the quantities of constants. Here you can see mass is 750, frictional constant is 30, applied force 300, spring constant 15, r is 1. So here you can, r is basically this y. So here you can see we have written this equation, and now we are calling this equation right over here in the ODE45. Okay, don't get disturbed with this option command. I will let you know what this option command do. So just leave here and focus on, we have initial speed and position is 0, 0, and we are using time span limited 0 to 200, so it will give you the response between 0 to 200 values on time axis, and initial condition is 0 0. So this is the code for solving the mass spring. So when you run both the codes of example 5.1 and 5.2, you will get a graphical result with respect to, in the first case you will get velocity with respect to time, and in the second case you will get displacement with respect to time. Now we will discuss the commands which we left in our manual, like ODE45 and options command, stats on command. So objective was to analyze or implement or solve the mathematical model of any physical system. So we have this example, a mass attached to a spring. We applied one force, and on the opposite direction these two forces are acting on this mass, which is a spring constant and frictional force. So we use ODE45 to solve this these system and desolve. So ODE45 is basically stands for ordinary differential equation. It integrates a system of differential equation with a time span which is defined. You remember we defined 0 to 125 and 0 to 200 in the two examples. So these are the lower and upper limits with the initial condition of y0, and we have suppose initial condition 0 0 in both cases. So here we have to call the function which we have created, then we have to define the time span, and in the last we have to give the initial condition, and this command will basically solve the differential equation or integrates the differential equation and gives you a result. This command shows you a result in the graphical format, and it will basically gives you a result in a column vector. So as far as desolve is concerned, desolve also solve this equation with initial condition, but it will give you answer in the symbolic solution, like you will get numerical values or numerical answer. So these are the commands you can use to solve any type of differential or any order of differential equation. Next we have one command, that is the options command. We have relative tolerance, absolute tolerance, and stats on. Let me show you the command where we have used this options command, OD set relative tolerance, absolute tolerance, and stats on. This command will basically, this relative tolerance is basically nothing but it controls the number of correct digits in all solution components except two smaller than the absolute tolerance. So it will consider all the values correct which are not smaller than the absolute level. So here by default it's 1 exponent minus 3, but we can also change this value just to avoid unnecessary or very small answers in our solution. Absolute tolerance is basically defined as the threshold below which the value of the solution become unimportant. It is the least value which we can consider for our possible solution. So by default it is exponent 1 minus 3, 1 exponent minus 6, but we can change it according to our requirements. Third one is the stats on. Stats on is by default is off, but if we write it on, so it will give the number of successful steps, number of failed attempts, number of times the ODE function was called to evaluate. So it will give you the inner properties, values of the inner properties of the ODE function command. So these are the commands. I hope these commands are clear to you all, and In the last we have an exercise. In exercise you can see there is a picture given in figure 5.2. Here you have mass attached with a spring, and forces are also labeled frictional force and mass displacement function with a constant b. You have to derive its mathematical equation by using the same above method we have discussed and solve it on MATLAB. So pattern will be followed same. You have to just keep in your mind what we are doing in the examples. First implement the examples and then implement the exercise in the same way. So you have to use ODE function or ODE solve to solve this problem. If any questions, we will schedule a session to take your online question and answer for further clarification. Thank you.